Lab for Oscillations. Introduction. So the purpose of this lab is to gain a deeper understanding of oscillatory motion exhibited on a mass swinging on a spring. By analyzing the behavior of this mass spring system, we explore the fundamental physics concepts such as energy conservation, oscillations, and forces in motion. So we look at spring force in terms of Hooke's law with F equals negative kx, and the gravitational force, which constantly pulls downward. And we also look at the fundamental concepts of kinetic energy, potential energy, which includes gravitational potential energy, with G P equals mgh, and spring potential energy given by SP equals 1 half kx squared. And we also keep the keep it in an ideal system where the total energy remains constant. Review of our results. So our analysis revealed that the total energy of the system remains relatively stable over time, confirming that the principle of energy conservation within the mass spring system. Although both measurements indicate periodic motion, a slight discrepancy was observed between x and y period estimates. This difference aligns with the additional gravitational force acting on the mass, which slightly influences the vertical motion. Minor deviations from the model and observed data may be due to experimental limitations. System and experimental setup. This system involves the mass suspended from a vertical spring that can oscillate both vertically and in an arc, as seen as the image below. This creates a complex two-dimensional oscillatory motion influenced by both the spring's restoring force and the gravitational force. Modeling approach. Initial velocity. This was calculated based on the displacement between the first two data points in the experimental data, ensuring that the data's model starting motion matched the video observations. And these are the three images that on the areas that I changed for coding, especially for system mass, the system timing, and the calculation for it. Changes in the system. We track three main energy components: kinetic energy, gravitational potential energy, and spring potential energy. The total energy was the sum of all components, ideally constant over time if the energy is conserved. The stable total line suggests that our model closely aligns with the theoretical expectations for a closed system, validating the accuracy of our setup and coding approach. Metal data and model predictions. So the oscillation period for the x position was longer than that of the y position. This can be from many factors, as the gravitational force, which the gravitational pull might affect the vertical oscillations differently from the horizontal motion, and the damping effects if applicable. Any minor damping due to air resistance or friction at the pivot point could also contribute to differences in the oscillation periods. This was minimal in an idealized setup. Sources of error. So some sources of error could have been the calibration of the tracker software, where we could have done it incorrectly. We also assume that there's no air resistance. It's a perfectly elastic spring, and there's no damping at all, as mentioned before. The impact of these errors could be that the kinetic energy of the potential energy calculations might misrepresent the energy conservation principle, suggesting energy is not conserved even though it should be. Questions? So, what if we increase the mass attached to the spring? Increasing the mass would likely lower the oscillation frequency, resulting in longer oscillation periods due to the greater inertia that must be overcome by the spring force. So, what does it mean if the model and the data show discrepancies? Discrepancies may indicate areas for improvement in experimental setup or assumption in the model. They can also prompt further investigation into external factors affecting oscillation, such as damping or external forces. Conclusion. So the energy principle was upheld as the total energies of the system remain stable over time. While oscillation periods derived from X and Y position data were comparable, some discrepancies were noted, and the interplay of kinetic energy and position energy during oscillation illustrated the dynamic nature of mechanical systems and reinforced the principle of energy conservation. Thank you for your time.